Hello everyone. So let's talk about the fluid mechanics interview preparation. So what is the meaning of fluid and the solid? So fluid, in this case, the molecules free movely and they also collide. Collide is the key word. And while in the solids the molecules do not collide, they can't move, but they can vibrate at the same position like this. They vibrate. Here the pressure term, as a pressure term, is caused due to the intermolecular collision. Where there is intermolecular collision, there is a pressure, and thus pressure is only applicable for the fluids. Molecules of the solid cannot collide, so the pressure term is not applicable for the solids. Fluids can apply pressure on solids, while solids cannot apply pressure on fluids or solids. Pressure is not applicable for the solid. Okay. Next is, when force is applied on the fluid, they flow, while when the force is applied on the solid, they undergo deformation. So there is a deformation, the strain is created. Due to the strain, stress is created. From the stress, we can actually calculate the strength of the material. So in fluid, stress is due to the intermolecular attraction or drag. In solids, the stress is due to the induced stress is due to the deformation in the body. So fluids, they are incompressible because the density doesn't change, while solids, they are compressible comparatively. So next is, what is mechanics? So mechanics is a field of study of the object which is moving or will move. It is the study of the object in rest. Sorry, which is moving or will move. In fluid mechanics, there are basically four parts: fluid properties, statics, kinematics, dynamics, and fluid machinery, which is extra. So what is statics? Statics is the study of fluid at rest. Okay, the study of fluid at rest. What do we study? We need to study the statics because to study the energy of the fluid at rest. Pressure energy depends on its position. If the fluid is rest, it does have some energy, and the energy depends upon the position or the height or the orientation of the fluid. Okay, so this has the potential energy or the pressure energy, so called. And in the statics study, we actually study about the hydrostatic law and Pascal law. So in the study of fluid at motion, there are two types: why the motion is happening and how the motion is happening. In why question, the dynamics part comes. In how question, the kinematics part comes. So in why, what is the cause of the motion? So dynamics explains the cause, that can be the pressure difference or the gravitational potential difference. Okay, and in the how does the fluid move? So it moves because of certain parameters involved in it. For example, velocity, acceleration, momentum, discharge, etc. So in these two cases, in these two fluid in motion case, we will study about the Bernoulli equation and the Euler equation. Okay. So Newton's second law is actually involved in this fluid mechanics. The fluid second law says that the force is basically the rate of change of momentum. So momentum is m times v. So rate of change of momentum is mv by dt. So in solids, its mass concept is involved, while in fluid, mass flow rate concept is involved. So in solid, the mass is basically constant, and dv by dt is basically the acceleration. So F is equal to ma for solids, while mass flow rate is involved in the fluid. So that means the velocity is considered a constant. There is a mass flow rate and the mass is changing. So mass flow rate is density times the discharge. So, and the discharge is equal to area times the velocity. So when we put this whole value here in the force, we get density times area times the velocity square. Okay, so in this case, the v square, which is the kinematic component, is basically the input, and F is the force, is the dynamic part, which is the output. This can be vice versa. Okay, it basically depends upon the application we are using. In sometimes the dynamic part can be input, and in sometimes the kinematic part can be input. So next is stress in fluids or solids. So fluid, we are restricting it to liquids because we won't be studying about anything which are compressible, which has compressible behaviors. That means the density is changing. So in liquids, the density doesn't change, it is incompressible. So in liquid, Newton's law of viscosity is applied. So this is the formula of Newton's law of viscosity. So the drag or the shear force is equal to the coefficient of viscosity times the velocity gradient here. So coefficient of viscosity nothing but the intermolecular attraction of the behavior, which is also the resistance created by the fluid for the flow. So the stress in the liquid is due to the intermolecular attraction, which is the mu, coefficient of viscosity. Then the shear stress or the drag, shear force or the drag force is shear stress times the area. So in liquid, we first find the shear stress, then find the force. But in solids, we first find the force and then find the stress. It's in reverse, okay? So next is the fluid properties. So in fluid properties, the first one is specific weight, which is equal to weight by the volume. So mg by v, m by b is density, so it is rho times the g. Okay, so why do we need it? Specific weight are used to calculate the power and pressure, etc. As pressure is equal to rho g z, density g and z, and same for power it is times the discharge. Okay, so second property is specific volume, which is equal to volume by mass. So v by m is equal to 1 by rho density. And why do we need it? For liquid, the specific volume is greater than 1. That is, for the liquid, the density doesn't change with respect to the pressure. For the gases, the specific volume is less than 1. So from this, we can easily identify that this is a gas material and it is compressible, as the change in density is non-zero. Third property is specific gravity. Specific gravity is nothing but the ratio of the specific weight of the body by the specific weight of the reference body, that is rho g by h2 rho g. So it's basically the density of the body with reference body. Okay, the density of the H2O is 1. The specific gravity of H2O is 1 because density by density of the same material is 1. Okay, so why do we need it? Specific gravity tells whether it will float or sink in the water or the fluid, any particular fluid. So if we consider the water, the specific gravity of ice is 0.9, that means 90% will sink, 10% will float like this. If it is wood, that means 60% will sink, 40% will float. If it is 1, that means it will sink and float inside the water. It won't sit in the water, but it will sink and float inside the water. Next one, what is the reason behind the Dead Sea? Dead Sea is basically found in the Israel, and due to the high evaporation rate, the sea has become very salty. That means the specific gravity is very high. The specific gravity of the Dead Sea is more than the specific gravity of human, and as humans have a specific gravity more than water, as humans have more specific gravity than water, that's why we sink inside the water due to our knowledge of learning to swim. So we basically swim. Otherwise, you can see that monkey basically sink because it has specific gravity more than 1. And for buffalo, elephant, you can see they float because they have specific gravity less than 1. Okay. So next property is the viscosity, which is a very important property. Viscosity, or basically we can call it the fluid friction. So the reason behind fluid flow is due to this viscosity property. It is basically the fluid friction. It is the property of the fluid which resists the movement of one layer over the other. So from this diagram you can see that this is the surface which has some friction, and this is the velocity profile. So due to this friction, the velocity at this point will be 0, and the layer above will have more velocity, and above it will just increase with the distance. So due to this friction here, the flow will be like this. Okay, at this point will be 0, and the top point is basically free stream at y maximum. Okay, and this property, this velocity profile is basically parabolic in profile. Okay, so du by dy, du is basically the velocity. So the change in velocity with respect to the depth is called as velocity gradient. Okay, so next is the movement of fluid layer causes shear stress to each other layer, which creates the shear stress. Okay, and according to the Newton's law of viscosity, as the movement of the layer creates a shear stress, that shear stress is basically proportional to the velocity gradient, and this proportionality constant is nothing but the viscosity coefficient. Therefore, the shear stress is equal to coefficient of viscosity times the velocity gradient, and the drag force is shear stress or drag times the area. To find the drag force, the process is, first we need to know the fluid property, that is the viscosity. From that we will find the after that we will find the velocity gradient, and from that data we will find the stress and then the drag force. So basically in solid, if you have the shear force here, from that shear force we will find the shear stress, and the shear strain will be deformation along the x-axis by the deformation along the y-axis, so x by y. And relation between this shear stress and shear strain is given by the modulus of rigidity. That means this is the relation equation here. Okay, in liquid it doesn't deform, it basically flows. Okay, due to the shear stress it flows, and from this profile you can see that this is the easy way of doing it. Let's consider the velocity profile as linear. So sorry, not linear, means if we consider the velocity from the axis, x-axis and y-axis, so this is the deformation like this. Dx by dt is equal to velocity. So rate of shear strain, the rate of shear strain is x by y times dt, which is basically du by dt. The rate of shear strain is equal to the velocity gradient, and as shear stress is directly proportional to the velocity gradient, from this we get the Newton's law of viscosity. So next is the graphs for different materials. So those whoever follows the Newton's law of viscosity are called Newtonian fluid, which has the proportionality straight. You can see it is a straight line, linearity. It means shear stress is directly proportional to the velocity profile. And for other graphs like this, it is basically pseudoplastic materials, for example milk, and the relations are something like this. And other graphs are diluent sugars, and the relation is something like this. So from this graph we can basically calculate the velocity dynamic viscosity. The tan theta is equal to dynamic viscosity, and then from this, if we have such a graphs, we can find easily from this that the viscosity of this curve is more than this b, because the slope of a is more than slope of b. That means the viscosity of this is greater than b. So coefficient of viscosity has two types. One is the dynamic and another is the kinematic. So dynamic viscosity changes significantly with respect to the temperature, while the kinematic viscosity doesn't change significantly with the temperature, and kinematic viscosity is equal to dynamic viscosity by the density. Okay, so next is how viscosity or dynamic viscosity changes with temperature. So in liquid, the dynamic viscosity basically depends upon the intermolecular attraction. If the temperature increases, the attraction between the bonds gets looser, so the attraction decreases, thus the dynamic viscosity decreases. For the gas, the dynamic viscosity depends on the collision of the molecule. So when the temperature increases, the collision increases, same way the dynamic viscosity increases for the gas. The bulk modulus, as we have seen the strength of material, bulk modulus is nothing but the change in pressure by the change in volumetric strain. So when the pressure increases, the volume reduces. So as we know that in the liquid the change in density is 0, that means negative change in P by 0 is equal to infinity. 0 is equal to infinity. That means change in pressure in a liquid doesn't change the density, so the bulk modulus is basically infinite. And from the relation that the compressibility is equal to 1 by bulk modulus, so we can easily know that for the liquid the compressibility is 0, that means it is incompressible. And from this is a material property, a liquid fluid property, that for liquid the bulk modulus is infinite, so it is highest, then it is solid, then it goes to the gases. So for isothermal cases where the temperature is constant, from the gas constant equation we can see that PV is equal to constant, and from this relation we can derive that the bulk modulus is equal to the pressure, so K is equal to negative P. Okay. And then the other fluid property is surface tension. Surface tension is nothing but the tension force which acts on the surface of the fluid interface due to the cohesive force of the liquid. So there is a cohesive force, there is the H2O bond which is very high here. So this basically attracts or pulls the molecule on the surface downwards. So this kind of phenomena creates a tension here over the surface. It basically behaves like the stretched membrane. The surface behaves like the stretched membrane under tension. So the interface can be between the anything two immiscible liquids or the air water. So any interface here. Okay. So the next is the intermolecular forces. So there are two kind of intermolecular forces. There is a cohesive and the adhesive. Both are basically attractive in nature, pulling, and it creates tension. So in cohesive is that the molecules are similar, that is H2H2 or the mercury, but in the adhesive there are dissimilar molecules. That means there are different gas or fluids involved. For example, H2 air or H2 glass or solid. So from the property of the particular liquid, let's say for water, glass and water adhesive force is greater than cohesive force, and it is greater than the H2 cohesive force is greater than the adhesive force of H2 and air. And for the mercury, the cohesive is very high, less than the adhesive force. So from this physical property, we can see that when we put a mercury on the surface, it becomes like a bubble while the water spreads out. So the reason behind is that the cohesive force of the mercury is very high than the adhesive force. Okay, and due to this high cohesive force, the surface tension is also very high. That is why the angle of contact is greater than 90 degree. And due to the higher cohesive force, it creates less wetting or spreading. While the adhesive force of water is greater than the cohesive force, that's why it spreads. And due to this adhesive force, the surface tension is less, and it creates acute angle. So from the tube, you can see that in the glass tube, if you pour a water, it creates a concave shape, and if you put a mercury, you will create a convex shape. This is the reason. The reason is due to the adhesive force between the water and the glass, it creates a curve like this. While there's a cohesive force, very high cohesive force, it creates a convex shape for the mercury. Okay, that is the reason specified here. So what is the relation between the temperature and the surface tension? So what happens if the temperature increases, the cohesive bond decreases. If the cohesive bond decreases, then the surface tension also decreases. Okay. Then the fluid property, surface tension. The stress is equal to surface force by the length. So we have the surface force formula. Surface tension force formula divided by length is basically the surface tension. And we can also calculate it another way. Surface energy divided by the surface area will give the surface tension. So why do we get spherical shape for the fluid like H2O? Why do we have a spherical shape? If we leave it, why do we get a spherical shape? The reason is behind that due to the cohesive force, there is a surface tension over the bubble. The surface tension is created due to the cohesive force. So to reduce the surface tension, what happens is that to reduce surface tension, we need to decrease the area. So if we want to decrease the area, we have surface energy formula like this: U is equal to tension times the area. To be in equilibrium, the fluid must have minimum surface energy as well as the minimum surface area. To have minimum surface area, the only thing satisfying this both condition is this spherical shape, which has less surface area as well as it can create less surface energy also. That is why the spherical shape is created. So what is if we have a spherical shape like this, so what is the excess pressure created inside the bubble? So there is a surface tension over outside. So due to this surface tension, extra pressure is created inside the bubble. So what is that extra pressure? So the fluid, due to the surface tension, tends to collide or accumulate, and they try to form a spherical shape. That is with minimum surface area to reduce the surface tension. Okay. Due to the surface spherical shape, the excess pressure is developed inside the spherical fluid. In equilibrium, the outer surface force should be equal to the inner body fluid pressure. So outer surface force is nothing but the stress times the area, stress times the length, means the circumference of this. The surface tension is this sigma times the circumference, that is the pi d, is equal to the pressure inside, that is P times the area of the intersection, that is the area of the circle. So if we equate it, we will get the force is equal to 4 sigma by d. This is the excess force inside the bubble. Therefore, the attractive surface tension force is equal to the separating pressure force. So this is separating pressure force inside. Okay. So next property is capillary. This is basically not a property, but it's a phenomena of that fluid which is related to the surface tension fluid property. So capillarity depends upon the adhesive and cohesive property of the fluid. Capillarity rise or fall of the liquid surface in small tube held vertically in the fluid. That height basically depends on the diameter of the tube, then the specific weight of the fluid and the surface tension. And the height formula is given from the ascent formula. So we will discuss what is ascent formula. So if we have a tube, a small tube, and in this we have a fluid. So you see that, for example, the fluid is H2O, and in this case it is a concave surface. For this concave surface, the contact angle is theta, okay, which is acute angle. And if you want to find the pressure at this level, the pressure should be same. Okay, so from this interaction, we will see that this small r is basically the radius of the tube, and this big R is basically the radius of the curvature of this meniscus. So the relation between this r and small r is basically from this angle theta. Theta is basically between this contact angle. The angle here and here will be same. This is the mathematical property. So cos theta is basically the small r by r. From this we get this relation. So d is equal to d by cos theta. So as we know from this property, we have concave meniscus. That means we have concave meniscus. It means that there is a very high adhesive force. If you have a high adhesive force, that means the surface tension is less. If the surface tension is less, that means the pressure here is less than the upper pressure. That means pressure here is less than the atmospheric pressure. Okay, from this relation we will get the excess forces this, and from this excess pressure we can actually calculate the pressure difference. So the pressure here is atmospheric pressure is equal to this one. So here the pressure is P atmospheric pressure minus the pressure here plus the height of the fluid. So from this we will get the height h as this. So this is the height of the capillary. So this is proper phenomenon of the capillary. Okay. So next is, if we have a flat meniscus like this, it means that both pressure, atmospheric pressure and pressure here are same. And if we have a concave, that means the atmospheric pressure is higher than the here, less surface tension. If you have a convex, it means pressure is higher than the atmospheric pressure, that means cohesive force, high surface tension. So the capillary height is this. So the thing is that the diameter of the tube, if it is infinite, if the diameter is infinite, that means the height is 0. That means it will have something like this, meniscus. So if we have a tube like this, and if we cut it here, and if it is a water, it will have a concave kind of meniscus. If we cut it tube here, what happens is that the pressure is high here at this point. Okay, what happens is that it will create a convex kind of shape. That means the pressure here is high. Okay, that is why it creates a convex kind of thing. Pressure is high, there is a high cohesive force. Okay. Next is application of the surface tension. For the paints, the surface tension should be less, so that it becomes sticky. There should be more adhesive force, it becomes sticky. For lubricants also, it should spread and stick, so surface tension should be less. For digital also same thing. It should wet the cloth. For that you should have higher adhesive force, surface tension should be less. For flex, that means for welding time we use the metals which are in molten state, and when we throw it around the other surface, it should stick. That means that adhesive force should be high, surface tension should be less. For the dirt, same thing, it should spread. That means the adhesive force should be high, surface tension should be less. For the blood, it is same thing. For the blood to flow easily or spread easily, the surface tension should be less. It should be more adhesive. And when we have a cut, that's why the blood comes out. and sudden and after, due to the chemical property of the blood, it clots, so the blood doesn't flow further. If you see a frying pan, if you use frying pan or the non-stick thing, for the frying pan it is the oil water interaction, that means um, the cohesive force of water is higher, that's why it creates a droplet. And for the Teflon, same thing, the water cohesive force is higher than this Teflon water, that's why the droplet forms. Okay, next one is the as we seen the difference between the pressure and the stress. So pressure is basically due to the intermolecular collision, which happens only in the fluid. It isn't is not applicable for the solids, as in solid the collision of particles doesn't happen. So always the pressure is compressive and it's normal to the surface, like this, as you have seen further. And the difference between the unit for the pressure and stress are basically same, Pascal and Newton per meter square. So for here the intermolecular collision, there is only external forces can be applied. It's only for solid, and this one for fluids. So this is only normal and compressive, but this one is normal and shear. In normal it is basically tensile and compressive. So basically the pressure leads to the stress. As you know, in the solids, stress is equal to force by area, but in the fluid you can see that the pressure is on the surface of the metal for the cylinder, and this pressure creates the hoop stress and the longitudinal stress, and the hoop stress is twice the longitudinal stress. So the equation is that pressure is equal to force by area, but the pressure doesn't depend upon the force applied as well as the area. If the area is high, the pressure doesn't decrease, or if the applied force is high, the pressure doesn't increase. But the pressure force is equal to pressure times the area. If the pressure increases or the area increases, the pressure force also increases. Okay, thank you.